So welcome back, guys. We have been discussing oscillations and we have found the expressions for displacement, velocity and acceleration of the particle. Correct. Now since this particle is in motion, right, oscillatory motion, it will have certain energy, right? Now certain mechanical energy. Now what are the forms of mechanical energy? Now one type is kinetic energy, the other type is potential energy, correct? So there will be some kinetic and some potential energy, and then of course there will be some total energy, right? Let us see how to evaluate these two types of energies and then total energy, correct? Now we have seen that my displacement is equal to a sine of omega t plus alpha, then velocity is plus or minus omega root over a square minus x square, where x is your displacement and capital A is the amplitude of motion, v is the velocity, and acceleration is of course minus omega square into x, correct? Now what is this omega here? Omega square, omega is equal to, or omega square is equal to k upon m, right? So that k, which is the force constant or spring constant for that matter, it is m omega square, right? Now I'm just writing down this a few parameters here which would be useful in the expressions for kinetic and potential energy, correct? Now here my velocity is plus or minus omega root over a square minus x square. So obviously my kinetic energy, it is equal to half into m v square, and that is nothing but half into m. So now here v square, it is going to be equal to omega square into a square minus x square. I'm just removing the root sign here because I'm squaring both sides, right? So it would be omega square into a square minus x square. Now m omega square, is it not k? Correct. So it is equal to half k a square minus x square, and that is nothing but my kinetic energy. That is the expression for kinetic energy. Now you'll be able to visualize here very clearly that when the particle is at mean position, my x, the displacement from the mean position is 0, correct? So my kinetic energy at mean position is going to be equal to half k into a square, okay? But when I am at the extreme position where my displacement is equal to amplitude, so my x is going to be equal to a, so a square minus x square is going to be equal to 0, and then kinetic energy at extreme position is going to be equal to 0, isn't it? And that matches with what we experience in case of a pendulum, correct? When the bob is at the extreme position, it stops there momentarily and then moves back, isn't it? Its velocity over there, it becomes 0 and it gets reversed. That means its acceleration at the extreme position is maximum, correct? And when it is at mean position, the velocity is maximum, and because of that maximum velocity, it moves further to the other side, on the negative side, correct? So this makes perfect sense so far. Okay, let us see what is potential energy. I'm just making one small sketch here. This is the mean position, let us call this position O, and this is the path. Okay, let us call AB as the path of oscillation, correct? So OA is equal to OB, and this is equal to capital A. Okay, maybe instead of calling this AB, let us call this PQ. So there won't be any confusion between this A and that A. So PQ is the path and A is the amplitude of motion at any point here, anywhere. Okay, I'm not taking any specific point, okay, but then I'm taking this displacement x over here, small x. Now you would say, what is the reason for this? Okay. Now the reason is when the particle is at position x here, my restoring force is going to be equal to F, okay? And if K is the force constant of the system, then I can say that F is equal to minus K into X, correct? Now, so this, we have this expression, alright? Now what happens is I'm considering a small, infinitesimally small displacement dx, maybe on this side here, and so this is dx. Dx is very small, infinitesimally small. Okay, now here what is going to be the work done by this force here? Now if you see the displacement dx, it is towards right, correct? And the work done by the restoring force is going to be opposite to that, isn't it? So the work done dw would be equal to minus of this force F into dx. And what is my F? F, is it not minus kx? So it is minus of minus kx dx. So that would be equal to kx dx. So my dw, that infinitesimally small amount of work done in getting displaced on the right side, okay, through dx, is equal to dw, and that is kx dx, correct? Now what? Now I don't want this infinitesimally small work done here. I want the work done, correct? So what do? I integrate. So I'm going to integrate here and here, right? So my w is going to be equal to, now integral x dx. See, k is constant which will come out of the integration sign, correct? So it is going to be equal to k integral x dx, and integral x is x square by 2. So it is going to be half into k into x square, correct? So now this work done is stored as potential energy, correct? It is this potential energy which gets added as the particle goes to the extreme position, and then you know what, when it reaches this point q, now that potential energy will eventually get converted back into kinetic energy, and the particle will be brought back towards mean position, right? So this work done is nothing but my potential energy. So I would say here PE is equal to half into k into x square. So I have kinetic energy is half into k into a square minus x square, and my potential energy, I'll call this 1 and I'll call this 2 here, and if I add both of them, 1 plus 2 implies my total energy is equal to, now here if you open this bracket, okay, it is going to be half k into a square minus half k into x square. So half k into a square minus half k into x square plus half k into x square, this potential energy here, total is going to be equal to half into k into a square, correct? This is the expression for total energy of this particle performing oscillatory motion. Now one thing is that here if you see k is constant, k is a force constant or constant for the oscillating system, okay? A is what? A is the amplitude of oscillation. It is the maximum displacement from the mean position, correct? So obviously my half k into a square, okay, it is going to be constant. The total energy of this oscillating particle is going to remain constant. Isn't that fantastic, right? Because if you see here, the kinetic energy, it changes as your x changes, your kinetic energy changes, okay? As your x changes, your potential energy changes, but then total energy of oscillation for this system is going to remain constant, okay? In the next video we are going to continue with these two or rather three expression for kinetic energy, expression for potential energy, and expression for total energy. We will we'll go in detail, what happens at each position, okay? And then we will move further to graphical representation of this kinetic and potential energies of this particle. Thank you so much.